Welcome to the Real Python Podcast. This is episode 128. Have you used a memory profiler to gauge the performance of your Python application? Maybe you're using it to troubleshoot memory issues when loading a large data science project. What could running a profiler show you about a codebase you're learning? This week on the show, Pablo Galindo Salgado returns to talk about Memray, a powerful tracing memory profiler. Pablo developed Memray while working at Bloomberg to track memory allocations beyond Python code into native extensions and the interpreter itself. It's a compelling tool to help you understand where memory is used by providing fine-grained reports. Pablo shares the different types of output Memray provides, including live mode, flame graphs, and a pytest plugin. We also discuss how a tracing memory profiler can help you understand a new code base. He walks us through how he developed the first prototype internally and eventually moved the project into open source. This is the first part of my conversation with Pablo. In a couple weeks, I'll share the second part where we talk about Python guilds inside large companies and his work as the release manager for Python 3.10 and 3.11. This episode is sponsored by Deepgram. Deepgram is the preferred speech-to-text API of Python developers. Get accurate transcripts from any audio with features for understanding. Try it by transcribing 200 hours free at deepgram.com/realpython. All right, let's get started. The Real Python Podcast is a weekly conversation about using Python in the real world. My name is Christopher Bailey, your host. Each week, we feature interviews with experts in the community and discussions about the topics, articles, and courses found at realpython.com. After the podcast, join us and learn real-world Python skills with a community of experts at realpython.com. Hey, Pablo, welcome back to the show.
Hey, thank you very much for inviting me again. It's a pleasure always to be here.
It was really fun talking to you at PyCon, and you had mentioned to me as we were kind of walking down the hall how you had just released this memory profiling tool, Memray, and how you were like, I was just on the show, would you want to come back on? And then I kind of never got back to you over the summer, sorry. But I am very excited to have you on to talk about Memray.
And I'm super excited to talk about it and maybe a bunch of other things at the end.
Yeah, that sounds good. I always have trouble sometimes talking about very specific tools. I kind of like to break it apart and generalize it.
Right.
So I'll make sure I kind of do a little bit of that in that case. But maybe we could start there. Where does a memory profiler kind of come in the workflow or the day-to-day of like a developer? Like when does somebody need to look at using that?
Right. I think it's an excellent question. So a memory profiler, like almost any profiler, is a tool that you will not use every single day. It's a tool that you can probably put into the bag of debuggers. Debuggers and profilers is normally the kind of bag that one puts this tool into. And in particular, a memory profiler, you will use it when your program is using a lot of memory, which always depends on the system you are. Maybe, if you are a super big company and have 1 terabyte of RAM in every server, maybe it's not the same kind of problem than if you run your program in your laptop, right? That maybe has 16 gigabytes, right? But anyway, normally if your program is using a lot of memory and you don't understand where that is coming from, or maybe you want to, you understand probably where it's coming from, but you want to try to see how you could reduce that, then you will go and fetch one of the memory profilers, and that will tell you in different ways. We can cover what different profilers can give you, but a memory profiler will basically tell you where your program is allocating memory, and most of the profilers will actually focus on the moment your program consumes the most memory. So, which is normally called and referred to the high watermark.
Okay.
So basically, the moment your program has more memory being consumed, at that point it will take kind of like a photograph of how the program memory is laid out, and it will tell you, okay, this piece came from here, this piece came from here, this piece came from here. So you know what parts of your code were allocating memory at the time that happened.
Okay.
Obviously, that is just one possible question that you may ask these tools, but normally all the questions and all the answers that these tools will give you are around how your program is using memory, right?
Okay, yeah, that makes sense. One of the ways I thought about using it was over the last several conversations I've had on the show, I've been kind of delving into the abstract syntax tree, kind of led or came from some of the conversations I had with you talking about, how the grammar is kind of working and so forth. But in this case, lately, I've also been talking about the stack trace and as the program is running and going into it. And I noticed that this particular profiler, or one thing that's really neat about it, is it gives you a very detailed list of like everything as it's going, which I don't know if that's directly one of the outputs is this nice thing that you guys have, which is called a flame graph, which I wasn't familiar with what that was.
Right.
And so maybe we could talk about that, the idea of this being more fine grain.
Right. I think it's a super interesting observation. Actually, in that sense, our profiler is a bit different from other profilers that you may find. I wouldn't say better because, and I think this is another. I'm here. I think it's a point that I would like to make. I think it's important to understand that different tools will serve you in different ways, right? And there is a lot of projects in the community, not only in the memory profiling space. This also happens on other areas like performance profilers, right? And there is a lot of people that kind of like to see one against the other. Oh, this tool is better than this tool. In general, I think that's the wrong way to look at it. Different tools will serve users in different ways, and different tools have different advantages and disadvantages and compromises. And I think it's important to point out which ones will help you to do this thing, but also that you could use some of them. So in our case, our profiler focuses on some things and try to do a bunch of things very well. But if you are not interested in those, you can use some others. And this will come in the future when I refer to the capabilities. But going to answer the question, so our profiler in particular, what it does is a bit different from what other memory profilers do. And what it does is it basically records every single allocation that your program does. This is already, if you do this or not in your profiler, this segments your profiler in two big groups. The first group is what is called a tracing profiler, which is what Memray is.
Okay.
Other profilers like Field, for instance, are also tracing profilers. So these tracing profilers basically trace your program, and every single time your program does an allocation, it records it. So it knows every single thing that happens, right? Obviously, this comes with a price because allocations are something that happens quite a lot, and if you do a bit of housekeeping every time there is an allocation, then it will be a bit slower. And then there is a lot of other profilers that are. This is kind of more common on the CPU and performance space, but it's also possible in memory. That is called statistical profilers, or more commonly sampling profilers.
Okay.
What these do normally is that instead of tracing every single function call and every single, in the case of memory, every single allocation, they do it statistically. So instead of like going every single time this happens, they sample the application. Like imagine, for instance, that you are doing some work, right? And then I will call you every 5 minutes.
Okay.
And every 5 minutes, you need to tell me
how's it going.
Right, how is it going? In fact, like I'm a crazy manager, right?
Yeah.
So I will tell you, hey, what file are you working on? And then you will tell me, oh, I'm working on test.py. And I say, okay, test.py. And, I called you like 5 minutes afterwards. And maybe you work a bit on code.py, but now you are back on test.py. And then you will tell me, oh, test.py again. So I will annotate test.py. And at the end of the day, I will kind of, see what files you were working on, and statistically I will tell you that you were working probably on test.py 80% of the time, and code.py 20. That doesn't need to be super close to reality, because I just called you every 5 minutes, and it could be any other frequency. I could call you every hour, right? And it will be a bit less accurate, but it will involve much less overhead, because I'm not calling you every single time you change the file.
Right.
In the case of memory, it's a bit more complicated, because instead of checking what the program is doing every 5 minutes, because that will have a problem, right? Imagine that I check what the program is doing every 5 minutes, or maybe I check every fifth allocation or something like that. That will be a bit problematic if you decide to allocate let's say 1 gigabyte in one go. I don't know. Imagine that your program says, "Oh, I need a super big NumPy array," and then you allocate 1 gigabyte. If for whatever reason my sampling rate didn't happen on that time, I will lose that gigabytes. Right? I will not report it.
Right.
So what memory profilers that are doing sampling do is that they kind of do some statistical sampling based on the bytes themselves. So they see the allocations not as events, they see it as a stream of bytes, and they do a statistical process called Memray sampling on those. The important thing at the end of the day is that it's still statistical. It won't be exactly how your program allocated, or they won't see every allocation. They will give you a good estimate.
Yeah. Okay.
And what you're trading here is performance, because they're normally faster because they don't involve this big overhead, but they will be less accurate, especially if your program does a bunch of like super quick allocations in weird patterns, because then the statistical approach will break. So anyway, that's kind of the background. Memray is a tracing profiler. So Memray sees everything. And the other thing that it does that is just, I think, nobody else does, at least in the Python world, is that it records everything and it dumps everything to a file.
Okay.
This is kind of different from other profilers, because other profilers, what they do is that they say, even tracing profilers like Phil, for instance, what they say is that, okay, I want to be, I'm a tracing profiler, but I want to be still as fast as I can. So what I'm going to do is that, okay, I'm going to see every allocation, but at the end of the day, I'm going to produce one single output. And it could be a web page, or for instance, Phil produces a flame graph, but others will produce something else. And what they do is that in memory, they will start aggregating that information into the format that they will output. And what this does is that they don't need to kind of remember every single thing that happened, because the only thing they need to do is build in memory this data structure that at the end they are going to show it to you, right? So this allows them to be a bit faster, because they will produce one single thing, so they can focus on that, and every single part of the information that is happening that they don't really need for anything, they will just drop it. Memray, instead of doing that, what it does is that when you run it, it just records every single thing that happens and puts it into the file.
Okay.
As you can imagine, this can create gigantic files, and at the beginning of the first versions of Memray, these files could be easily gigabytes of memory. Then we introduced super heavy compression, like 2 layers of compression, so now they are like quite smaller, like megabytes instead of gigabytes. And the interesting thing that we do is that once you have this file, you can analyze the information in different ways. So you don't need to rerun your program. You could say, okay, maybe I'm interested in this flame graph that you mentioned, right? So we can cover what the flame graph does, but you say, okay, I want a flame graph, and then you can grab the file and produce a flame graph, and that will give you, for instance, the what is normally referred to as the high watermark flame graph. But maybe you say, oh, now I want to see if there is any memory leaks in my program. So without having to run your program, you can grab the same file and say, okay, show me the memory leaks, and it will show you the memory leaks. And maybe you can say, oh, now I want to list the table of the 10 biggest allocations, and you can show the table of and you don't need to rerun your program.
So yeah, that's what I was wondering about. Like there are going to be times when you're running a program, potentially one time you're running a process, but I would guess there'll also be times where you would have something that's kind of continually running.
Right.
And in either case, you're able to output, because it outputs this like .bin file, this sort of compressed binary version of the thing that you can then use to do all these analysis processes, right?
Right. So, for instance, you mentioned something interesting, and this is a good opportunity to highlight the thing that I started. That also helps me, because otherwise it would be a bit weird that is without context.
Yeah.
So, for instance, Memray, being a tracing profiler, and especially since we produce these files that has a lot of information, basically all the information is every single allocation, function call, etc. So these files, even if we have a lot of compression, if you have a program that is running for half an hour or an hour, these files could be enormous.
Yeah.
Not only that, but analyzing this, even if you have the hard drive, I mean, maybe they are not that big, but like even if you have your hard drive to hold those files without a problem, analyzing them can be quite slow, because there is like gigabytes and gigabytes of information. So in this case, maybe a tracing profiler is not what you need. If you have a long-running application, maybe it's better to use a statistical profiler. For instance, another interesting profiler that is a statistical profiler that has some memory profiling as well is Scalene. I don't know how to pronounce it.
Okay.
Sorry.
It's like SCALENE.
Yeah, like the triangle, like the big side of the triangle.
Scalene or something like that. Yeah.
Scalene, yes, scalene. Sorry, apologies. My Spanish,
It's okay.
my Spanish is limiting me here. Scalene. Well, that's another example. But in that case, a sampling profiler will be a bit better because maybe in that case, you're not interested in absolutely everything that happened. If your program is regular enough, you will get enough, a close enough snapshot of what you are searching for without having to, record absolutely everything. So this is a good example of when you will go to a different kind of tool.
Okay.
Than Memray or other sampling, other tracing profilers. But yeah, that is kind of a unique approach. We try to do one of the kind of core things that our profiler does is that it records everything, so you can analyze the allocations in different ways. And there are very interesting things you can do once you have that much information that you cannot do if you don't have that. For instance, we have these other kind of outputs when you can say, okay, I'm interested on seeing, for instance, what we call temporary allocations. So temporary allocations are allocations that the next thing the program does is deallocated. So you allocate a big chunk and then you deallocate it.
Okay.
And these are interesting because if you have a lot of this, maybe it's going to be better for you to, instead of allocating and deallocating a lot of small blocks, maybe it's better for you to allocate a big one, and then instead of removing chunks and allocating bigger chunks, you just use it.
Because it's like can be kind of busy work of constantly pushing and pulling things in and out.
Exactly.
Okay.
Right. So imagine, for instance, you have a Python list, right? And it's empty. And then you start pushing things to it. So what is going to happen is that at some point the list, the list starts with a given size. This pattern also happens in C++ with vectors, and in many cases when you have like a vector or list kind of a structure. So what happens is that you start pushing things, and at the end of the day, at the beginning of the day, the list has a specific capacity, and once the list of the vector is full, then what will happen is that when you push another item, it will say, oh, I don't have enough space, I need to grow.
Yeah.
So what is going to happen is that it's going to allocate a bigger chunk of memory, it's going to copy the vector to the bigger chunk, and then it's going to deallocate the smaller chunk. And then if you start pushing elements, that is going to happen again. It's going to be full, and it's going to allocate an even bigger chunk. Normally this doubles, so it goes from 2 to 4 to 16, etc. So to 8 to 16. For instance, in Python, we do a slightly different strategy to grow, but normally doubles. So what happens is that it's going to start growing and growing and growing. And every time, it gets full, it will do this pattern when it allocates a bigger chunk and copies. But if the only thing your code does is pushing elements, maybe a better strategy will be to what is called pre-allocate. So you are going to say, okay, I'm going to need 1 million elements. So don't do this kind of business of like growing, copying, because at the end of the day, that is quadratic, because every time you keep pushing, you need to copy all the elements again, and then copy them again, and then copy them again, and allocate.
Yeah.
Right? It's quite bad. In this case, it's not bad for memory, because at the end of the day, the you need at least a vector as big as the elements that you want to push there. So it's not technically a memory problem, but it's a performance problem.
Right.
Because instead of doing this, allocating is quite expensive. So, and copying as well. So instead of doing that, what you can do is to say, okay, give me a vector of 1 million elements, empty, like without anything there. And then you start putting the elements, instead of appending to the list, you will substitute the elements that at the beginning they are not none or garbage or whatever. And then you will substitute them by your items. And in that way, you just allocate it one time. So Memray, one of the things that you can ask for it is to say, okay, tell me these temporary allocations. I want to see when my code is doing this pattern, for instance. So you can find these places when you are doing this kind of dance with memory, and instead of that, you say, I want to, maybe a better strategy here is to, allocate a bigger chunk and then reuse the chunk instead of, removing and adding.
Yeah, it sounds like you're really able to look at like different sort of angles of performance. I think of maybe like you'd have like all these kind of cameras and other tools for studying an athlete or something like that, and you're kind of like trying to figure out the performance of how that person's doing and how to improve on it.
Right.
In this case, you're able to kind of look at real fine-grained kind of stuff and kind of see, oh, okay, well, this is where these little problems are. Python developers from companies like NASA, Volley, and Spotify chose Deepgram's speech-to-text API for accurate, usable transcripts to power their voice bots, podcast analytics, and video platforms. Deepgram automatically transcribes any audio with understanding features like summarization, topic detection, and language detection, so you can do more with your voice data. Get an API key and transcribe your first 200 hours for free at deepgram.com/realpython. But one of the things I think is kind of interesting about it too is it has multiple sort of outputs. And we mentioned the flame graph a couple times, and I don't know if we defined what that is, because I was like kind of confused about it. I actually found like a little article about it.
Everybody, I think you're not the only one. Everybody is super confused with this output the first time.
How to read it.
It's kind of universal. It's kind of universal. Yeah.
Is that like, where did that come from? Like, is that a technique that's been around for a while?
Yeah, like the output, I think it was invented by a fellow called Brendan Gregg. He's, I think he now works at Intel in performance. He's very well known because he worked a lot with a Linux profiler called Perf.
Okay.
And he started doing he has a bunch of recipes and he has a lot of talks about Perf, and he investigated a lot of ways to report performance in tools. And he came, I think he was one of the first, maybe someone came with the thing first, but I think this was the term flame graph, at least was coined by him. Okay, anyway. So a flame graph is basically a representation. Normally is used for performance. So normally is used for knowing where your program is spending time, but you can use it also for memory. So the first thing that you need to be aware when you look at a flame graph is that the x-axis doesn't represent time, which is super confusing. So basically a flame graph is a bunch of blocks, and it will tell you a snapshot of a program. Or for instance, in the case of memory, it will be the snapshot of when your program is using the biggest amount of memory. So imagine that your program is running, and at the moment your program is using the most memory, imagine that you take a photo of all the memory of the program that is using at that time. And what the flame graph will show you is that basically every piece of that photo, where it's coming from. Right? So imagine that, you run your program, you wait, and let's say that the maximum memory uses is 1 gigabyte. So when your program reaches 1 gigabyte, then you take a photo of all the memory, of all the RAM that your program is using. And then you say, okay, where every piece of this memory is coming from. So maybe the flame graph will be able to tell you, okay, so 20% of the memory is coming from this function call, because this function call was allocating a NumPy array that is very big. And the 30% came from this import, because this import is I don't know, is calling deal open over a C extension, and it's a lot of memory. And the other 10% is actually 1 million calls to this function, something like that, right? And the idea is that the flame graph will basically segment that into chunks in a way that let's say two pieces of memory are allocated by the same function, they appear over the same block. So basically every block in the y-axis is a different function call level. So for instance, let's say the first block in the flame graph will be the root, that is the start function in your program. And then every block that is over the first one is a different function call. So for instance, you have a block, the first one, let's say, is a function called start. And there are 3 blocks that are over start. Let's call those blocks foo2, and foo3. Foo2 and foo3, sorry.
Okay.
This means that function start called foo2, foo3, right? So every block that you have above one given block is function calls that were called by the previous one. And so on and so forth. So you have a big tower, a bunch of chains function calls. And at the end of the day, the bigger the block, a given block is, the more, in case of memory, the more memory that block allocated. So you see a block that is very wide, that means that block in particular allocated a lot of memory. If that block has a block above it, it means that block is a function that call another function that in turn allocated something. Normally blocks, as they go higher, they become smaller, because obviously you have a function called that allocated 1 megabyte, and that function called 2 functions. So either the 2 functions are responsible for the megabyte when combined, or the function itself is responsible for most of it, but they cannot be more, right? Because a function can allocate as much as their children plus the function itself. So that's why it's called a flame graph, because normally what happens is that these blocks, it's like a bunch of towers. As you go higher and higher, the blocks become smaller and smaller. So if you kind of look it and squint a bit, they look like flames.
Okay.
That's why it's called a flame graph. Normally, in the case of memory, the metric that you're using is memory allocated. So the wider blocks, the more memory a function allocated. If it's a time flame graph, the wider the block, the more time your program spent in that function. So at the end of the day, if you find this explanation confusing, it's because it's quite difficult to explain it without a visual cue, right?
It is. It's a graphical thing, yeah.
Yeah. So apologies to our listeners.
The thing that it made me think of is I studied program management for just a little bit, at least understand what program management is.
Right.
And it kind of reminded me of the Gantt chart.
Oh, right. Yeah.
Of like allocating, again, resources.
In some ways, it's actually similar, right? Because at the end of the day, you have like things that combine into a bigger thing.
Yeah, like an overarching project and all the little things that need to be done within it. I mean, they're not exactly, but they're kind of akin to each other in a way. And
I think now that you mentioned the Gantt chart, I mean, maybe this is not the best comparison, but maybe it can help some users.
Yeah.
So I think a flame graph, a way to describe it is a combination of two charts. One of them is a pie chart, right? That basically tells you how the total segments over different pieces.
What's used what?
Right. In this case, imagine that the total is the RAM, the memory that your program uses when it's at its highest.
Yeah.
And it will tell you this piece comes from here, this piece comes from here, right? So that will be a pie chart. But because every segment of that pie is not just one label, so you cannot just say the function that allocated memory, because most of the functions are going to be called malloc. So you don't want to just a pie chart that says, 20% comes from malloc, 80% comes from realloc.
Right.
That is not interesting, right? You want to know who called that malloc, right? At the end of the day, okay, malloc, but who called malloc, right? Or maybe you have a factory function called create object, and then someone tells you, okay, 80% of your memory comes from create object, and you say, okay, yeah, that's nice, but who called this function?
Right.
So the pie chart is basically, it will tell you, okay, so this comes from here, this comes from here, but then the other chart that is being combined here is basically a stacked frame, right? Like a traceback. So imagine that you have this pie chart, and from every segment of the pie, instead of having just a label, you have an entire stacked trace. So like when you get an error in Python, it will tell you what function called what function.
Yeah.
Right. So it's the same. So instead of telling you just 20% of the memory comes from malloc, so instead of telling you that, it will tell you, okay, 20% of memory comes from malloc, but malloc was called by this other function, and this other function was called by these other two functions. And maybe you have 10 different functions that call malloc, but maybe one of the function called malloc 3 times and the other call it 1 time, or maybe one function called malloc with 6 million bytes and the other with 2.
Yeah.
So every segment of that pie will be entire stack trace of a given allocation or bunch of allocations, and they are basically structured in a way that you can see what function is calling what other functions. So you won't have different segments of the pie if you have common ancestors in the call tree. Again, without saying one, is quite difficult to know. So I will.
Yeah. I'll include links.
Right. I will advise our listeners to just look at it.
Yeah.
And we have in the documentation like a tutorial on how to understand flame graphs. So don't worry, if you say that it's a bit confusing the first time you see it.
Yeah.
It always happens. So you just need to get used to it.
And it's interactive in ways too, because you can kind of peel it apart and focus on specific things too. At least the HTML output version of it, you can kind of interact with it.
Yeah, you can search as well. Some people like to see it the other way. So for instance, this is kind of a funny term when people like to see it instead of like from the smaller chunks up and the bigger chunks down, when they want to see it the other way, like smaller chunks down and big chunks up, they call it an icicle graph. Because like icicles.
Oh, okay.
Yeah.
Stalactites and stalagmites,
right? Stalactites,
exactly.
Yeah.
Yeah, cool.
Yeah, that is quite cool. But yeah, that is one of the outputs. That is probably one of the more powerful ones. Other profilers, like for instance, Phil, do also flame graphs. This is a very good output because it will tell you a lot about where the memory is coming from, but it will tell you only the highest watermark. So it's only the memory when it's at its peak, right? So even if your program ran for 2 hours, it will just tell you one single point, right? That's so it's important, but it's not the whole picture.
Yeah, totally. You mentioned it a couple times, and I'll remind listeners that I had Idemar Turner-Trowning on the show, I think right about the time he was developing Phil. So quite a while ago, like a year and a half ago. So I'll include links to that as another tool that's out there.
Right.
One of the other tools that you're using, also kind of another kind of guest thing, is that you have a tool that allows you to see the profiler running in the terminal. And so you're using Rich for that, which is really kind of neat, to indicate stuff.
Yeah, and kudos to all the people working at Textual.
Yeah.
It's a fantastic tool, Rich and Textual as well. So we have a bunch of like terminal reporters, we call these things. The reason is because we have a bunch of them that generate web pages, like HTML files that you can kind of look at your browser.
Yeah.
But there is a lot of the time that is not super convenient. Maybe a lot of people run this thing on servers or Docker containers when they cannot generate HTML files and look at them. So there is a bunch of these things that allow you to just get the output in the terminal. So there is something akin to a flame graph in the terminal. We call it a tree reporter, but there is also, for instance, a table in the terminal using Rich. And one of the things that we like the most is that we support this mode called live mode. So this mode, what it does is that instead of running your application, generating the file, and then producing kind of like different reports, what you can do is that you can run it and attach the profiler to your program. And as the program is running, you can get continuous snapshot of what the program is doing. So instead of generating static reports at the moment the program reaches its maximum, it will tell you what the program is doing as it's running. So it's a kind of interactive and live dynamic mode. And it has this textual interface using Rich that will probably move to textual once that reaches a stable release. But at the moment we're using Rich, and it will tell you like a small graph in the terminal, and it will show you a table over what functions at a given time your program is they are allocating the most memory. So if your program, for instance, is a long running program that is running for a lot of time, a way to avoid having to reach for a statistical profiler is to use this live mode, because we won't generate the file. You can see what your program is doing in terms of memory allocation as it's running. So maybe your program reaches 2 different peaks and you want to analyze how it goes from one to the other. So the live mode is a way to do that.
Yeah, it's nice.
It's interesting because apart from the outputs, one of the things that allows us to do these kind of things is that we do an interesting approach that many other profilers don't do this. So when one of the important things when you're doing memory profilers is that you want to see all allocations, right? So not only the allocations that come from Python code, you want to see all of them.
Sure.
So this is kind of a bit complicated because Python has a bunch of ways to interpose memory allocators. So you can ask Python using the C API to say, okay, every single time you use one of the APIs to allocate memory that Python uses, kind of call me back so I can do a bunch of a bunch of bookkeeping. This is what tracemalloc does. Tracemalloc is a standard library module that allows you to do like some memory profiling. But unfortunately, this only works for Python allocations that are made by the Python interpreter or C extensions using the Python interfaces. This is by memmalloc, by memcalloc, and all these. But if you bring a C extension that doesn't know about Python, or maybe it does know about Python, but it doesn't really care, like NumPy, for instance, or TensorFlow, or anything on C and C++, those C extensions, especially they are used a lot in the data science world, they won't use the Python allocators. They will use normal malloc, realloc, or if you're using C++, they will use new, all the C++ isms, right? Something like tracemalloc, or if you use one of these Python allocators, you won't see them. And those are important as well. So what Memray does 2 things that are unique to Memray. One of them is that it needs to see every single allocation. So profilers, to be able to do this, like profilers like Phil, for instance, or Scalene as well, they use something that is called preloading. So most operative, at least Linux and macOS, allow you to say, they allow you to provide a set object, like a file, that contains implementations of a bunch of functions that you want to use instead of the default ones. So, for instance, you can implement your own malloc. You have the same interface. Malloc takes a number, that is the number of bytes that you want to allocate, and returns a pointer. So you can implement your own version of that. You can actually use the regular one underneath, but you can kind of do extra things. And you can tell the OS, okay, so load this program, like Python, but every single time someone calls malloc, instead of calling the real one, call my version. That is called preloading. And in Linux is using an environment variable called ld preload. In macOS it works similarly, but it has two problems. The bigger one is that you need to modify how you launch your program. So for this to work, you need to export an environment variable and then launch your program, right? And in that way, you will point to where your special file is with your implementation of malloc, and then your malloc will basically register every single time that happens. That's how normally profilers do this. But this is kind of a problem. One of the reasons it's a problem is because this allows you to, this forces you to modify how your program starts. And this is quite annoying because you may not be able to control that, or this forces you to run the profiler across all your program, right? And that can be quite inconvenient. Like, imagine, for instance, that you are using your test suite, and your test suite, you can say, okay, what I want to do is run all my tests. And every single time I run one test, I want to profile that code and know what the test is doing in terms of memory.
Okay.
The problem with you do one of these preloading things is that you will also profile the test runner itself. So imagine you're using pytest, because you can only activate this thing from start to finish. You cannot activate it, let's say, granularly. You will pay for all the code that pytest is running that is not your test, right? Not only that, but you cannot easily deactivate it and activate it, because even if you deactivate it with some kind of boolean that, maybe does a bunch of if statements in your code to just call the normal malloc and don't do what your profile is doing, you will still pay for the indirection. So technically it will be slower. So what Memray does is that it uses a special mini linker. So we deal with deep shenanigans
Okay.
in the operative system. So we do like a small dynamic linker implementation that it's kind of a bit deep to explain here, but basically what it will do is that it will find every single time your code calls malloc, and it will rewrite the code on the run, and it will, instead of placing the memory address of the real malloc, it will replace that by our own version. But the good thing about this is that we can do this thing after the program started. So you can start your program as normal. Like, for instance, you can write pytest, and only when you want, you can say, okay, so for instance, one of the APIs that we offer is a context manager. So you can say, profile only this chunk of code. So what Memray will do is that only in that chunk of code, it will rewrite all the programs, so all the malloc calls go through us. And when it finishes the context manager, it will undo that. So it will rewrite all the program and it will put the real malloc back again. So when you are outside the context manager, you run as if nothing happens.
So that's all happening in memory, right?
Right, effectively. So when Linux, for instance, loads your program in memory, in Linux, the format is called ELF, stands for executable unlinkable format, which is quite funny because the debugging format is called dwarf, and it doesn't stand for anything.
Okay, they just liked it.
The only reason it's called dwarf is because it's funny.
Yeah. Some Lord of the Rings action.
So someone actually came with some retroactive acronym. I think now they say that is debugging with arbitrary frame.
Oh, it built a retronym.
Something, but it's after the fact. So it happens in memory. Like the Linux kernel loads the executable, these ELF files in memory in specific ways, and normally these functions go through something called the PLT. It's called the procedure linkage table. It's a special indirection table that is used to load dynamic objects and things like that. And what we do is that we go through all relocations, so not only PLT relocations, but also other kind of relocations. What relocation means here is a bit tricky to explain, but it has to be, like, I will need to explain how Linux loads programs, and that will take me a while. But the idea here is that we will find every single place that your program uses to call these functions, and then we will rewrite it, which is a very similar thing that the linker does when you use this preloading mechanism. But instead of having to do it at the beginning of your program and having to stick with it forever, we can do it on the go, right? So we have our own mini implementation of that, and we support both Linux and macOS. We don't support Windows.
So those are platforms where you can accomplish some of these fancy tricks that you're talking about.
I'm sure we can do it in Windows as well, but I think it's just too much. And I'm particularly not an expert on Windows, so I wouldn't know where to start. But I can do it on Linux and macOS.
Yeah.
But yeah, that's kind of a unique thing that we do. You can activate this in, and this allows us to do a bunch of cool things. For instance, you can have many people have like a signal handler on the program, and you can send a signal to your program, and it will automatically activate Memray at that time, and it will start profiling your program, and then you can, for let's say 10 seconds or 15 seconds or a minute or whatever, and then it can deactivate the profiler, and it can run as if you are not profiling the code, so it will run as normal, so you don't pay for having a profiler over there. So that's quite cool because it allows us to do all these dynamic analysis that you can activate, and then when you are done, you can go and continue as normal, so you don't need to modify anything. For instance, we have this pytest plugin that you can just install, and then you can just run pytest normally, and it will, every time pytest calls one of your tests, it will automatically collect a bunch of metrics over your code, running Memray automatically for you. And at the end of the pytest run, it will tell you, okay, this test is using this much memory, and this other test is using this much memory. And you can do cool things like saying, okay, I want this test to fail if it uses more than 5 megabytes.
Okay. So you can set new parameters.
Right. So even if your test succeeds, if it uses more memory than you want, you can force it to fail. And the cool thing is that this doesn't take a lot of time because it only activates the profiler around the code that is running under the test, not by the test suite itself. Like pytest code runs normally. So that's one of the cool things that we do. The other cool thing that I think is is unique to Memray is that we also report native allocations. So other profilers can see them. So Phil and Escalin and some others can actually see that a malloc call was made. So they see all allocations. But the thing is that they can only tell you what function calls in Python lead to that call.
Okay.
And that sometimes is enough. Most of the time is probably enough because you can see, okay, maybe when I added these two NumPy arrays, something allocated, I don't know, 10 gigabytes of memory.
Yeah.
But sometimes it's not enough because sometimes what happens is that the Python call is called run. And then there is a lot of C and C++ code or Rust code or whatever code underneath that has a bunch of different things, right? For instance, maybe you're using SQLite 3. We have an example in the documentation about SQLite 3. And then you do a query, like you do SQLite 3 run, or I don't know how is the interface, but you do like a query in SQLite, and that query allocates, I don't know, 10 gigabytes of memory, and then you say, why? So what Memray will do is that apart from the Python functions, it will tell you also the C functions. So you can see exactly what is happening underneath that Python call, and you can see that, actually those 10 gigabytes are coming because it's doing a B tree, right? Like databases normally uses B trees, among other things, depending on the database. But you can see that maybe, it's creating these structures and it's using it in this way. So maybe you can go and allocate. And if you're using, data science or machine learning or things like that, it will tell you exactly what in the underlying C and C++ code, or it can be anything for it. It can be Rust or it can be Java or whatever. As long as it uses Dwarf, this debugging information, we can see it. And you can see like, this Python function called this C function, that in turn would call again this Python function. So you can see the whole stack, what we call the hybrid stack between C and C++ and Rust or whatever, and Python. And you can have a super cool, perfect picture over who is calling who and who is allocating memory in a way that is probably much richer, especially if you're using C extensions.
Yeah, that sounds really powerful. This week, I want to shine a spotlight on another real Python video course. It's titled SQLite and SQL Alchemy in Python, Moving Your Data Beyond Flat Files. The course is based on a real Python article by Doug Farrell, and the instructor is my frequent co-host, Christopher Trudeau, who shows you how to use flat files such as CSVs for data storage, the basics of relational databases, how to start with a single file format SQLite for data storage, and how to use SQL Alchemy in several ways, including core text, core statements, and how it can behave as an object relation mapper, or ORM, helping you to work with data as Python objects. I think it's a good investment of your time to learn how Python, SQLite, and SQL Alchemy can give your programs database functionality, allowing you to store data in a single file without the need for a database server, and how an ORM can help you get past needing to learn the intricacies of SQL to start working with the data directly as Python objects. Real Python video courses are broken into easily consumable sections, and where needed, include code examples for the techniques shown. All lessons have a transcript, including closed captions. Check out the video course. You can find a link in the show notes, or you can find it using the enhanced search tool on realpython.com. To kind of go in like a different direction, I kind of started on this path like really early on in our conversation about the idea that maybe you could use it as a tool. I mean, obviously you can see how your program is working and, you know, kind of what it's doing, where the memory allocations are happening, if it's traveling into, okay, here it's talking to the database, but now you can actually see like where, you know, what's happening a little deeper inside that. But I thought it could be a neat way to learn more about, like, if you're somebody who's coming to Python and wanting to learn like kind of how this sort of stuff works, like, you know, not only like what often, you know, people open up a debugger to kind of just see where the path of things are going. What a memory profiler, or in this case, Memray, could do for you is give you, not only is that call happening, but this is what memory is being called and kind of where these other performance hits are. And I think it might be kind of a useful way to learn maybe better techniques in your programming. Like,
Right.
one of the things is obviously you don't want to have problems with running out of memory or seeing memory leaks and things like that, but also just like general performance.
Yeah, and I think this is a super important point that you're making here, that profilers and debuggers are not only things that you will use when you have a problem, right?
Yeah.
Like, they're super interesting tools to understand more about your program, right? In mind that I think you described it in a fantastic way. You have a kind of a, imagine you join a team or something, and then you have to learn this big application.
Yeah.
You're not going to sit down, right? You're not going to sit down and read the whole code base, right? That will be crazy. But maybe you want to know. So maybe you want to know a bunch of like what is the 90% important things that this application is doing. So an interesting way to do that is that, okay, I will just run for instance, my CPU profiler. So you use let's say Austin or PySpy or whatever you want to use, and you run it over your code base, and it will tell you, sure, I mean, your program is gigantic, but 80% of the time is spent in this function.
Right.
So you say, okay, better read that function, right? Because
I should look at this thing. Yeah. Okay.
Right. So in the case of a memory profiler, what we will tell you is that, okay, maybe we cannot tell you what functions are the most important, but we will tell you, okay, these functions are using the most memory. So that can tell you many things about your program. For instance, that can tell you the data structures that your program is using come from these functions. So you can go there and say, oh, I understand, that this function, this code base is dealing with, I don't know, graphs, and these functions are creating those graphs. Or it can tell you that, it's doing a bunch of machine learning, but the tensors are, I hate that word, by the way, as a physicist, that is super inaccurate, but I will say it for the advantage of everyone listening, because they probably don't care about the inaccuracy. But they will tell you where this let's say multidimensional arrays instead of tensors.
Yeah, there you go.
Yeah, it's a bit of my thing. But anyway.
It's okay to have pet peeves.
Right. People like to just make me angry just by saying tensors. But yeah,
Okay.
it doesn't matter. It's just like all physicists, we are a bunch of weird people and we get angry very easily. Anyway, it will tell you where your tensors or matrices or whatever are being allocated, right? And then you can say, okay, I can learn more about how my program prepares all this memory. Or maybe it will tell you about, oh, we are doing this kind of like super quick allocations because maybe we are, creating this big other thing about using small pieces. So I think you have a fantastic idea there that I will encourage a lot of people that need to deal with like learning a new code base,
Yeah.
or learning more about their code, because you will certainly be surprised a lot of the time, right? Like the same way with people are, they jump to Python and then they say, oh wow, doing loops is quite slow compared to other languages, right? There is this tweet by John Carmack, the creator of a bunch of games like Doom and things like that.
Yeah.
He was like ranting a bit about how like he's a super good programmer, but he comes from like a C and C++ background, and he was like super surprised about how quote slow close quote Python is doing loops, right? Especially compared with C and C++. I mean, there are reasons for that, right? Like Python is a dynamic language, and et cetera, et cetera. I mean, and John Carmack knows this. It's just that he was surprised of how much difference there is between C and Python, like more than 100 times. But the same surprises probably will come with memory. You will see that operations that you think are super, trivial actually spend a lot of memory, or the other way. Maybe.
Right. What's the thing? You can make that really bad decision to start working on part of the code with just this sort of assumption. It's like, well, this is what this is, because a person named something, like it's named a particular thing, but without actually watching it run. I think I've said this before when I was talking about debugging, where I used to do this thing where I was a consultant and I would watch the person for just a few minutes, just like, okay, well, I know you're having a problem. I know you want me to fix it, but can I just watch what you're doing and how you're doing it? And you just immediately see like, okay, well, okay, this is plugged in backwards, or, whatever it is, like kind of thing. Like you can kind of very quickly talk about audio. Like there's a common problem that people have with creating feedback. They don't understand the whole gain structure. And so they're like, boosting the signal like crazy, like at different wrong places. And it's like, you're literally making a distortion pedal here because you're like amplifying it way too early. And it's like,
man, for me, especially I think as a physicist, that thing happened to me a lot of the time. And it's a bit, crazy, because you will say, oh man, but you're a physicist, you should understand all this circuitry, right? Like you have, I have at least 3 like subjects in university that start with electronics, right?
Sure.
But it's, these layers are, so deep sometimes that is extremely non-trivial to use all the knowledge that we have, and we end doing stupid things like putting a lot of gain when we shouldn't, right?
Yeah.
Like one of the latest one that I had to deal with is that my audio interface has this button called INS that stands for instrument.
Sure. Okay.
And what that does is activate high impedance, right?
Yeah.
And I was thinking, well, high impedance sounds bad because that is like, a lot of like, it will make my signal more difficult to pass through. So why I want that? Like that will reduce my gain and my volume. I don't want that. But it turns out that especially you using an electric guitar, you absolutely want. I mean, was many years ago. I'm not that stupid now.
I mean, it's where do you learn those things,
But I was thinking, man, exactly. But I was thinking, Jesus, I mean, this doesn't make any sense because like I want, if I want a higher signal, I don't want like to make like the circuit to make the electricity be more difficult to pass through this, right? So why I need this? And it turns out that the answer obviously is not that easy as like, Ohm's law, right? It's more complicated because, you need to deal with the fact that you need to match the impedance of the guitar, because it's not the current that you are measuring, is the voltage, right? And then you need to, for maximum transmission, you need to match. So, these layers start to go one up to the other. I was one of those people that were making a distortion pedal out of their audio interface just because
it's easy to
and
do.
also like instrument, like what is an instrument? Because if you have a keyboard, it doesn't go into that way, right? A keyboard doesn't; it goes a line input, so you don't want high impedance. I don't know. So it's complicated, right?
Yeah. Well, I like learning about kind of the different ways that you can use these things to kind of teach yourself some more. I mean, that's one of the main goals I have across the podcast is just like, let's learn a little more about what's going on. I kind of wonder, and I was wondering about like your process of where did the tool come from? Because like one of the things I thought also was interesting, I'll include this link to this Bloomberg blog post. It sounds like it was an internal use only tool before. Is that right?
It was. Yes.
Okay.
So what happened here is that I work at Bloomberg in my day-to-day work. By the way, I'm quite happy that just as a so I always struggle to say this word, shout out. Well, anyway, they are nice enough that they allow me to work part-time on Python. So thanks to Bloomberg.
Yeah.
So being said that, one of the things that happened is that Bloomberg is a financial company and whatnot, and most of our code base we used to be a super big C++ house, so C++ only, right? We deal with like fast things. So what happened a lot over the years in the whole world in finance and Bloomberg as well is that we started to use a lot of Python actually, because it turns out that we care about nanoseconds. It doesn't apply to all the code base, right? So yes, we have a lot of hardcore C++ engineering and whatnot, and we have a lot of nanosecond kind of application, but not everything is that, right? Actually, most of the things are not that. So it turns out that Python is very interesting to glue all these things together, or maybe for the things that are not that important, you can use Python to orchestrate your C++ code. So what happened at Bloomberg is that we have a lot of C++ wrapping Python. So you have a bunch of Python, which is the same thing as most of the data word in Python, right? Like TensorFlow, Keras, NumPy, Pandas, all of that thing is C++ and C and Fortran wrapped in Python. So yes, you are adding NumPy arrays, or you are calculating this back propagating whatever in machine learning, but at the end of the day, there's a lot of C++ code running underneath, right?
Yeah.
So a lot of our developers, so I work in the Python infrastructure team. My work at Bloomberg is basically to make sure that Python users in the company have the best tools and the best Python, etc.
Okay.
So one thing that happens is that a lot of users were telling us, hey, we have this kind of problem because we have to deal with this brutal amount of data, and we're using all this Python code to deal with that. But it turns out that all the tools that are available out there to solve memory problems, they cannot tell us anything about what's happening in C and C++, and we have a lot of that, right?
It's sort of invisible.
So yes, yeah. So they come to us and say, look, man, I'm using these other profilers, and they are telling me that most of my memory is allocated in a function called run.
Yeah.
And there is only one. And and we say, okay, that sucks. So what they wanted is this kind of hybrid like C and C++ plus Python view. And there was nothing around that. Like one of the things that we do at Bloomberg a lot, and we put a lot of emphasis on our team, is that if there is a existing ecosystem or an existing tool that does this, instead of reinventing the wheel, we try to actually not only adopt that, but also contribute back. We believe a lot in open source. We wouldn't have done that if we thought that there was not a space for some innovation. So we developed this. Actually, the first version of this tool was not called Memray; it was called Pensive, because I don't know, Harry Potter memory sounds cool.
Okay.
It was quite popular inside, and a lot of people were using it. And at some point, I don't know who it was. I think one of my managers mentioned, like, actually, why are we only using it at Bloomberg? This could be super cool to give back to the community, because it actually feels a need that is quite common. And yeah, I said, sure. And then we renamed it to Memray because Pensive was already chosen on PyPI, so we couldn't use the same name.
Okay.
And we open source it. And it turns out that, indeed that was filling a big void because it became super popular. Like we had almost 5,000 stars in 1 or 2 days. It was quite crazy.
Wow. That's great. I think a name it fits because like you think of like X-ray glasses or whatever, like the idea like you could actually look deeper than just the Python layer. You're actually like seen the frequencies beyond that.
Right. I was a bit afraid at the beginning with the name because I said like, oh man, I was so used to the previous name.
Yeah.
Man, now I really like the new name. Like we even have t-shirts with this.
Okay.
Yeah, quite cool.
What's a cool logo? I don't know who came up with the logo.
So it wasn't some like we pay some person to design it, and
nice.
Yeah, I'm not good at all on graphic design.
No, it's my problem.
It's like it's a weird like the logo is like a mix of a snake and a dragon, right? Like a lot of people say like, it's a snake or a dragon. It's like, I don't know, it's like a snagon.
Yeah.
But thank you. I also think it's a cool logo. But yeah, that's where it came from.
So like, what's the time frame? Like you had that internal tool. How many years? Like, kind of where's the time allocated there as far as like it kind of getting developed and coming out?
I made the first prototype in a week or so, and the idea was if I was able to do two things. One of them is to do this kind of a special linker kind of thing that will rewrite your memory stuff. That was unclear if I could pull that out in a performant way and stable enough without hacks. And the other thing is that I was a bit concerned that, gathering all these C and C++ allocations sounds super cool, but it's not easy. Not only is not easy, but also is slow. And actually doing all that as the program is running, I was thinking that it was going to be too slow. The actual way we do that is that we gather just enough information so when you generate the report, we can resolve it at that time. And I did that prototype in kind of a week or two. And then after that, we started developing the thing. In our team was mainly me and two more people. One of them is my team leader called Laszlo. And then Pradyum, I don't know if you know him. He works a lot on PIP and PyPA. So we developed the first version that was productionalized.
Okay.
And then since we started to think, that was done over a period of 4 or 5 months. And we started to use it for the first time kind of in production environments like 6 months after inception. And after that, I think it was like 2 more months, and then we open source it. And since then, I think it has passed like 1 year and 2 months or something like that. But one of the things that we do a lot that I'm quite happy is that not only we have open source the tool, but we have moved the development to the open source repo.
Oh, cool.
So we don't develop the tool anymore inside. So if you go to Memray, the repo, you can see me and my college. Now is Matt Wozniacki and me. So me and my college working on it mainly. But we do it in the outside open source repo. So you can see every conversation that we have, and you can see how we work together and like what are our decisions. And so we don't have Pensive anymore internally. What you see in the repo in Bloomberg/Memray, the GitHub repo, is what it is. And internally we use literally the same thing.
That's cool.
I think that's quite cool because you can see literally how we work. So if you're interested in seeing like how people work at Bloomberg, you can literally see it happening in real time.
Yeah, it's nice. So Pablo, I want to thank you for coming on the show and sharing all this information about Memray and memory profilers with me. We're going to continue the conversation in a follow-up episode. We're going to talk about some other things, but I really want to thank you for coming on the show this week. I
want to thank you all for inviting me and our listeners for able to withstand me talking for a lot of time. So I hope that everybody had interesting time listening how profilers are made, and it's always a pleasure to be here.
All right.
Right.
And don't forget, Deepgram is the preferred speech-to-text API of Python developers. Get accurate transcripts from any audio with features for understanding. Try it by transcribing 200 hours free at deepgram.com/realpython. I want to thank Pablo Galindo Salgado for coming on the show again this week. And I want to thank you for listening to the Real Python podcast. Make sure that you click that follow button in your podcast player. And if you see a subscribe button somewhere, remember that the Real Python podcast is free. If you like the show, please leave us a review. You can find show notes with links to all the topics we spoke about inside your podcast player or at realpython.com/podcast. And while you're there, you can leave us a question or a topic idea. I've been your host, Christopher Bailey, and I look forward to talking to you soon.